Hey everyone, and welcome back to the channel. For decades, humanity has peered into the cosmos, slowly unraveling the universe's grand narrative. We've mapped galaxies, probed distant nebulae, and even glimpsed the faint afterglow of the Big Bang itself. Our understanding, meticulously built on a bedrock of physics and observation, culminated in what we call the Standard Model of Cosmology. It's a beautiful, elegant framework that explains almost everything we see, from the largest structures to the smallest particles. Then, just a couple of years ago, a new eye opened in space, an eye designed to see the universe's earliest moments, to witness the birth of the very first stars and galaxies. And what it saw, what the James Webb Space Telescope has revealed, has sent ripples of exhilaration and confusion through the scientific community. It's not just showing us new things, it's challenging the very foundations of our cosmic understanding, hinting that the universe's story might be far stranger and far more ancient than we ever dared to imagine. In fact, many scientists are now openly asking, did the Webb telescope just break physics? To understand why Webb's observations are causing such a stir, we first need to grasp the cosmic story we thought we knew. Our prevailing understanding is encapsulated in the lambda-CDM model, where lambda represents dark energy, the mysterious force accelerating the universe's expansion, and CDM stands for cold dark matter, the invisible scaffolding upon which galaxies are built. This model paints a picture of a universe born from the Big Bang about 13.8 billion years ago. In its earliest moments, the universe was a hot, dense soup of particles. As it expanded and cooled, matter began to clump together under gravity, primarily guided by the gravitational pull of dark matter. The very first stars, theorized to be massive, short-lived population III stars made almost exclusively of hydrogen and helium, ignited only a few 100 million years after the Big Bang. These stars then forged the first heavier elements, seeding the cosmos for subsequent generations of stars and the eventual formation of galaxies. According to this model, the early universe, say, within the first 500 million years, should have been a relatively sparse place. Galaxies would be small, irregular, and dim, just beginning their journey of growth and assembly. They would be like cosmic toddlers, taking their first wobbly steps. The James Webb Space Telescope, or JWST, was specifically designed to peer back into this cosmic infancy. Its enormous 6.5-meter golden mirror, and its exquisite infrared instruments allow it to capture the faint, stretched-out light from these extremely distant and ancient objects. Because the universe is expanding, light from distant galaxies gets redshifted. Its wavelength is stretched, moving it from visible light into the infrared spectrum. Webb, orbiting far from Earth at the L2 Lagrange point, is shielded from Earth's heat and light, allowing it to perform this incredibly sensitive infrared astronomy. It was built to find those very first, small, nascent galaxies, to observe the cosmic dawn, and confirm our models of how structures formed in the early universe. But almost immediately after its first full-color images were released, Webb started sending back data that contradicted these long-held expectations. Instead of small, dim, irregular protogalaxies, Webb began to find a surprisingly high number of incredibly bright, massive, and seemingly mature galaxies existing at staggering redshifts. These galaxies were observed when the universe was only 300 to 500 million years old, a mere blink in cosmic time. Think of it. The universe was just 2% to 4% of its current age, and these galaxies already looked like fully formed cities, bustling with stars, showing signs of complex structures, and containing far more mass than our models predicted was possible for that epoch. One of the most striking examples came from the GLASS survey and the JWST program, which identified galaxies like JWST GS-Z13 to 0 and GLASS Z12. These aren't just one-off anomalies. Webb is consistently finding these cosmic titans across different fields of view. The sheer abundance of them is what's truly baffling. Our standard model suggests that at such early times, the universe simply hadn't had enough time to build such massive structures. Galaxy formation is a hierarchical process. Small dark matter halos attract gas, forming small galaxies, which then merge and grow over billions of years. To have so many large galaxies so early implies an accelerated formation process that current physics struggles to explain. So what does it mean for Webb to have broken physics? It doesn't mean the Big Bang theory is wrong, or that gravity suddenly stopped working. Instead, it means that our detailed understanding of how structures evolve within that framework might be fundamentally incomplete, or, at the very least, needs significant revision. One major implication concerns the ** speed of galaxy formation and star formation efficiency. For these early galaxies to be as massive and luminous as they appear, they must have formed stars at an incredibly rapid pace, far exceeding the rates predicted by our models for the early universe. It's like finding a fully grown adult born just a few years ago. Where did all the raw material, the gas, come from so quickly? How did it cool and collapse efficiently enough to form so many stars so fast? Our current understanding of gas dynamics and star formation efficiency might be inadequate for these extreme early conditions. Another area of challenge relates to asterisk dark matter halos. Galaxies form within massive halos of dark matter. For a galaxy to be as massive as those observed by Webb, its host dark matter halo must also be incredibly massive. Our lambda CDM simulations predict a certain distribution and abundance of dark matter halos at different epochs. The problem is, these simulations don't produce enough of these massive halos at such early times to account for the number of large galaxies Webb is seeing. This could suggest that either our understanding of dark matter's behavior in the early